So let's just start this video, and in this video probably we'll be able to solve all the questions that have came in the NEET, in all the previous year questions that has came in NEET. Probably after solving this session, or after completing this session, you'll be able to solve all those numericals or all those questions that have been there in the previous year examinations, right? And the first thing that I want to tell is that the prerequisite for this session is that at least you should know, I'll be covering all the exceptions that is coming in our way, but at least you should know what are the class 10th basics, right? You should know about the class 10th basics, as well as you should know what are the regular trends, right? So you should know regular trends as well. So if you know these two things, you are good to go for this session, right? For example, what can be a class 10th basic trend? For example, the atomic size we know, right? For atomic size we know that the atomic size, when we are going across a period, right? When we are going across a period, atomic size decreases. When we are going down the group, atomic size increases, right? Actually, I'm having little cough, so maybe it will be difficult for me to pronounce everything loudly. So may my voice comes little slow. Sorry. So this is, I think, the basic thing that you should know, what is the regular trend of atomic size, and rest you don't need to cover by anything into this chapter. Just cover these exceptions and you'll probably be able to solve all the questions, right? So the first exception arises in atomic size. The first exception is that this exception is something which you have to learn it directly. Then I'll tell you some conceptual exceptions as well, and I'll tell you some exceptions that you have to learn as it is, right? So first exception that we are going to encounter is the size of oxygen is quite greater than nitrogen. For example, the regular trend of the atomic radius says that when we are moving across a period from left to right, so the size usually decreases, right? So from that analogy, we can see that the size of nitrogen should be greater than that of oxygen, since oxygen lies more onto the right most of the periodic table. But this is not the by reality. In real observations, the oxygen is found to have the more atomic size than nitrogen, is slightly larger than nitrogen. So this was our first exception. This is something that you have to remember it directly, and abhi tak to question nahi aaya, but there are chances that question come. And second thing is you don't need to mess up lot about the NEET is actually an easy examination compared to other competitive exams. So इसमें भी exceptions के जो level हैं, they are not that much by hi-fi, ठीक है? Next exception is the exception of the gallium. Then we have gallium in our list, right? And gallium, we can say since we know that when we are moving down the group, right? So let's say I am moving down the group in the boron family. So what is going to happen is the atomic size usually increases. So boron should be having more size than aluminium, and aluminium should be having more size than by gallium, and gallium should be having more size than indium and then thallium. This is going to be the actual order, but actually it's not true. Let's say when we are looking into the real order, the aluminium needs to be small than gallium, but that's not true. Gallium is actually bigger than aluminium, right? So this is the one exception in the boron family when we are talking about the atomic size. So the atomic size have two exceptions directly, right? The first is that oxygen is greater than nitrogen, and second is that gallium is greater than aluminium. Next exception is of lanthanide contractions only, but these exceptions are also of atomic size, and lanthanide contraction is going to be the application, right? And what is the application of those exceptions in atomic size is the reason is lanthanide contraction. Let's see what is lanthanide contraction. So contraction is something when let's say this is in circle, and there are some circumstances that happen, and after that the size of circle gets shrinked, right? So this is something that we know that it is contraction. Now we're going to know about the size, okay? why when there's some specific atoms get contracted and their size decreases. So the actual reason is due to the shielding effect. For that we need to cover the shielding effect well, right? Although we are not by going into we are not going deeper into the concepts, we are just trying to learn the exceptions, but this is by little important. So let's just see the first concept of the what we say shielding effect. For example, let's say we have the nucleus at the center. Let's say this is the nucleus, right? And then we are having the electrons in the orbit, and there are multiple orbits in an atom. I will not be able to let's say draw every electron in the orbit, but let's just say I'm drawing some random electrons. So let's just say these are the electrons which are there in the orbit, right? So let's just say the atom, we know that the like pools and repel each other in physics, right? For example, if there's a positive charge or if there's a negative charge, they used to repel each other, right? So now our concern is that this is an electron, right, which is present in the outermost shell, and these are some electrons which are present in the inner shells. So the repulsion that these electrons generate on the outermost electron, that is known as electronic shielding, right, or shielding effect, right? You can say Z effect is there, right, or shielding effect is there, right? So this is actually the shielding effect. We used to represent it by a small sigma. Next thing that we are going to cover is that how lanthanide contraction take place. So lanthanide contraction is actually happened due to the poor shielding of the 4f electrons, right? So we have some 4f is a subshell. We used to know that f is a subshell, right, which used to have we can fill total 14 electrons into f, right? So and the elements in f blocks are known as lanthanides, right? Now we are going to learn that why the size gets shrinked. So actually what happens is that the 4f orbital used to का जो सबशेल होता है, they are not able to apply the good shielding effect. And what happens when they are not able to apply good shielding effect? For example, this is a nucleus, and these are by some orbits which are right, which are by located outside the atom. Let's say this, I'll not be able to maybe draw the complete orbit. For example, let's say these are the inner electrons, right, and there are some, let's say, inner electrons in the orbit, right? Let's say these circles, let me just draw it with some different color. So let's just say these red color by objects are nothing more than electrons, and let's say these are electrons, right? What is going to happen is, let's say this is an 4f subshell. Actually subshells are something, the parts of shells, so probably will not be able to draw them in the diagram, but let's just suppose these are f subshells and these are electrons, right? These are electrons. So since a 4f subshell is not able to shield the electrons, if the shielding is good, so there is some repulsion in the electron, and that repulsion causes the, if there is electron, that repulsion will cause some distance in between them, right? Since they are repelling to each other, so there will be a maintenance of a distance, right? And if the shielding is very poor, right, अगर shielding बहुत खराब होगा तो फिर ये जो electrons हैं अंदर वाले, they will not be able to push the electrons which are present in the outermost shell, right? So that was the concept of shielding effect. And if shielding is poor, so size will get contracted. Since electrons को उतना shield नहीं कर पाएंगे, so electrons will, if the shielding is poor, so electrons will come close to each other, and that is the reason कि their size gets shrinked, right? So that is the reason that जो 4f का वो होता है, क्या कहते हैं, जैसे कि जो हम लोग डाउन द ग्रुप जाते हैं, तो व्हेन वी आर गोइंग डाउन द ग्रुप द एटॉमिक साइज शुड increase, but when you reach this by 4D series, I think 4D series, 5D series, so probably the size did not get by decreases. The size of 4f and 5f is actually almost similar, right? And the reason is the contraction. Because of the contraction, the atoms get shrinked and their size decreases in reality. So that is about the concept, and now I have by some exceptions on this. The first exception is of yttrium. ठीक है, yttrium, the size of yttrium is greater than that of lanthanum. I think you should note all the exceptions right here. And when I used to prepare for JEE, I also have noted every exception in my notebook, and that was helpful for me in my examination. So yttrium, which lies above the group, is having more size than lanthanum. Let's just have a look at the periodic table. So this is yttrium, right, and this is your lanthanum, right. So lanthanum is also lying down the group, but the size of yttrium is greater than that of lanthanum. And when we are comparing lanthanum and actinium, the size are quite similar, right. Then we have zirconium and halfmonium. So let's say this halfmonium is having 4f orbital. I think I need to decrease the length of the pencil. Yes. So now just start it again. So let's just see the size of yttrium is greater than that of lanthanum. So this is something that also you have to note it, right. Next is the size of zirconium, okay, is almost similar to or almost equals to halfmonium. But actually when we are looking into the regular trend that we have studied already in our class 10, so that tells us that the size of halfmonium needs to be greater than that of zirconium, because we are going down the group, and when we are going down the group, so the atomic size usually increases, but it's not actually what happens, right. What happens actually is that the size of halfmonium is similar to that of zirconium, right. So this is something that you have to remember. And second thing is that the size of 4D series, means size of this series, is actually almost similar to size of this series. So this is also something that you can remember. And when we are talking about tellurium and zirconium, since there is no f spore shielding of f electrons or f subshells, right, or you can say the electrons present in f, right. That is the reason I pronounced it f electrons. So there is no shielding effect, so that is the reason we will be following the regular trend. And according to regular trend, the one which is situated down the group is going to be more in size. So that is the reason that titanium is lesser in size than zirconium, right. So that was about the exceptions in atomic size. You can just directly learn them. That will be, I think, best for you. And one more exception, I think we have boron, phosphor. No. I think that's it. Even theory, if you have to solve any questions on the behalf of atomic size and you have to differentiate them in behalf of atomic size, what you can do is first you just try to check out the shell numbers. If shell numbers are same, then check their charges, right. And if charges are there, if charges are also same, let's say they are all neutral, they are all positive, right. Say then check then what atom is situated more on the right side of the periodic table. In that we will be able to solve all the questions of the periodic table. I think I have told you the boron family's exception as well, that gallium usually have the lesser size than aluminium, right. That was all exceptions about I think these are all exceptions about atomic size and length and contraction. Our second topic is the ionization energy. Usually ionization energy used to have a lot of exceptions, but I used to solve them within concept of half filled subshells or full filled subshells. For example, if we are having P6, P3, or let's say we are having D5. I was not able to make D5 properly. So if we are having D5, if we are having D10, or sometimes even if we are having S2, means we are just completing the noble gas configuration state. So in all these states, to remove an electron from all these subshells, it's very difficult. So what you need to do is that the ionization energy of these subshells are drastically very high. So whenever you found something which are following these by configurations, you can just mention them as their electron ionization energy is going to be high. So let's just discuss some exceptions that occur and that you can solve on this concept is, for example, let's just take example of nitrogen used to have 2p3 in the last, while oxygen have 2p4, right? So in that way the ionization energy of nitrogen is more than that of oxygen, right? So that was the one thing, right? Similarly we can see that when we are going for magnesium, so magnesium usually is having 2s2, okay? So the magnesium used to have more ionization energy than aluminum. In same way you can solve these kinds of questions, right? So the one which are having the half filled subshells or the fully filled subshells, they are going to have the high ionization energy. For example, ki if I have, let's say, F negative, right? So F negative is there, or let's just talk about S2 negative and chlorine. So when we are comparing S2 negative and chlorine, so S2 negative here is completing its noble gas configuration state. So the ionization energy of S2 negative will be greater than that of chlorine, right? That may be an advanced question, but you can just solve all the questions based on this concept, right, very easily, because you just need to find out the electronic configuration and then probably you'll be able to solve all the questions. If you want to look some questions that what kinds of questions that does need ask, you can go on my previous video and I check out all the PYQs that came in last years, right? So that was about ionization energy. Achha, there was an very irregular order which was present in boron family. So I want you just remember that as it is. It is very, let's say if you are going to solve it conceptually, it will be very difficult for you to solve. So I just have an trick for this. You can just draw a W, right, and then start by mentioning all the elements which are present in the boron family. So first we have boron, then I think we have aluminium, and probably after aluminium you will have gallium, right? So you can just place gallium over there, and then we have tellurium, and then we have indium, right? So actually the ionization energy of boron is high. Then I have just drawn this W little incorrect. So what you can do is just make an aluminium little by above than this aluminium, this indium, right? So indium is going to be little more deeper. So let's just say this is the W that you have drawn, right? So first you have to mention boron, then aluminium, then gallium at the middle, then indium, and then the last element of this boron family, right? Up next is the first, which is having on the top we have boron, then we are having this tellurium, then we are having gallium, then we are having aluminium, then we are having indium. So this is something that you can directly remember. And boron, then we are having this last element of this boron family, then we are having gallium, then we are having aluminium, and at the last we are having indium, right? So that is the trick to remember this ionization energy for this one, right? The ionization energy, there is one more concept that in beryllium it's I think we have atomic number 4, so we are having the electronic configuration as 2s2. So probably if you are having the electronic configuration 2s2, it is actually it is fully filled. So the exception is that the beryllium is going to have the high ionization energy than lithium. In magnesium it's not there, probably it's not there, right? Because 2s2 is not that much strong, right? But when we talk about, let's say, Mg2 plus, right, so now it's very high. So ionization energy now is very high because it's now completing the by electronic configuration of neon. So if somehow the element is by attaining the noble gas configuration state, so the what we say so the ionization energy is going to be very high. So these are some exceptions that you can directly remember for ionization energy, right? Next, we are going to know about the highest ionization energy. The noble gases used to owe the highest ionization energy. The helium is the one which is the having highest ionization energy. Since we don't study too much about this series 7th period, and by that reference, cesium is the one which is having the lowest ionization energy. This is also something that you can remember. Maybe sometimes it can, why they can ask you this, right? Acha, this was actually true that the one I quoted. I'm sorry for that, but magnesium, since it has 2s2, so the ionization energy of magnesium is greater than that of aluminium, right? In reality, what it needs to be is that the actually when we are moving, let's say when we are moving left to right, so the ionization energy of aluminum needs to be more than that of magnesium, but that's not true. In reality, the ionization energy of magnesium is greater than that of aluminum, and same as for the beryllium. If we're comparing it with boron, so the ionization energy of beryllium is greater than that of boron. So this is also something that you need to remember, right? So whenever you are getting by these kinds of thing, when you are getting partially filled subshells or fully filled subshells, what your duty is to figure out that they are going to have more ionization energy. And these are some exceptions. The exceptions that I'm detailing in this class are the most important ones. You can just note them down, right? Next is the exception about, next is not exception, it's a regular trend. Next we are going to cover electron affinity. So electron affinity is, why we don't have a lot of time to cover what is electron affinity and everything, so we are just looking the exceptions into electron affinity, and for that I just need to remove everything from this, and then probably you will be able to just learn them, right? See, if you learn them right, it will take the least time, and that will be most helpful for you. So electron affinity exceptions are going to be like this. Let's say first just start with the second period. So we have boron, carbon, nitrogen, oxygen, fluorine, right? So let's just talk about these 5 elements. So we are talking about these 5 elements, and what we are going to do is we need to figure out that what is going to be the exception. In regular trend, we used to study that down the group the electron affinity decreases. So according to the regular trend that we studied in class 10th, according to that, the boron, carbon, nitrogen, oxygen and fluorine needs to have less electron affinity than needs to have more electron affinity than aluminum, silicon, phosphorus, sulfur and chlorine, because we are going down the group. But in reality, when you talk about, they are having more electron affinity, so you can just mark them or you can just remember them, they are having more electron affinity, right? But that is something which is exactly opposite to the regular trend, but that's the exception. We need to remember it, right? And one more exception is there when we are let's say talking about this boron family. So aluminum and then there is not exception. I think then there is regular trend, that the one which is located on the let's say top right used to owe the higher electron affinity. So this is a by sign, when the mouth where it's open, it's, let's say, it's a greater value, and where it is closed, it's a lesser value, right? So that's done. And oxygen has the minimum it's also a by direct exception. Oxygen although lies onto the top of its group, but this is something that you can remember directly, that oxygen used to have the minimum electron affinity in their group, right? For example, oxygen, yes, that's it. Oxygen has minimum electron gain enthalpy in their family. So although oxygen lies on the top, but it has minimum electron gain enthalpy or electron affinity, something that you can by recall, नेक्स्ट इज क्लोरीन, ब्रोमीन एंड क्लोरीन वाला एक्सेप्शन और ऑक्सीजन सल्फर वाला एक्सेप्शन तो ऑलरेडी हम लोग को पढ़ाया जाता है, ठीक है. So now just come to electronegativity. When you're, let's say, when you're by learning electronegativity actually a phenomena where it's the tendency of the atoms to attract the shared pair of electrons. What it can do is just directly remember a series that I'm telling. For example, the series says that fluorine is more electronegative than oxygen. Oxygen is more electronegative than nitrogen. Nitrogen is almost equal in electronegativity than chlorine. And then we have iodine, right? And iodine is having almost equal electronegative than carbon. Then we have phosphorus, right? And then we have boron, and then we have silicon. Okay, so we are going out of the screen. So then after boron we have silicon. That is the first order that you never remember. भाई इसके बाद all the questions that are coming in even in JEE you'll be able to solve them. Next, second order is that when we are comparing, aluminum is more electronegative than magnesium and then sodium. So these are some two series that you can just directly remember and your electronegativity stuff is almost completed. Next topic is the nature of oxides. ठीक है. अच्छा, हम लोगों को जो बेसिक थ्योरी पढ़ा है, ठीक है, उसमें ये पढ़ाते हैं कि जो एसिड्स होते हैं, ठीक है, दे आर एक्चुअली द ऑक्साइड्स ऑफ नॉन मेटल्स, राइट. एंड जो बेसेस होते हैं दे आर एक्चुअली द ऑक्साइड ऑफ metals, ठीक है. And that is somewhat true in the general conditions, in the most of the conditions, but we are going to learn about the exceptions. Acha, exceptions is there, but we have by solved a lot of questions by into the last lecture about the periodic table. So the many questions were there on to the amphoteric oxides. So now we are going to learn what are amphoteric oxides. First, there were some only specific elements which usually form amphoteric oxides. So those elements are osmium probably is Fe. Iron in the oxidation state of +3 forms an amphoteric compound. Then we have Sb, okay, in the oxidation state of 3+ only. So these are by transition elements. Then we have chromium 3+. Chromium usually show many by oxides. Then we have vanadium 5+. We used to study vanadium pentoxide a lot. अब वेनेडियम के भाई बहुत सारे कंपाउंड होते हैं, लेकिन जो एक ओनली कंपाउंड एम्फोटेरिक होता है दैट इज V5, राइट. नेक्स्ट इज वी हैव Te, and Te makes an amphoteric oxides in the +4 oxidation state, and osmium I forgot it's 3+, ठीक है. And we have zinc also. I think zinc one is very common. Everyone knows that ZnO2 is amphoteric, PbO2 is amphoteric, but these one are, let's say, someone which are rare and unique. Usually people forget them. अब इन ये जो मैटर्स हैं, ठीक है, तो इनके ये ऑक्सीडेशन स्टेट के जो ऑक्साइड्स हैं वही सिर्फ एम्फोटेरिक होते हैं. फॉर एग्जांपल कि AS2O3 ही एम्फोटेरिक होगा, Fe2O3 ही एम्फोटेरिक होगा और V2O5 ही एम्फोटेरिक होगा, राइट. तो इसके अलावा इनके जो दूसरे ऑक्सीडेशन स्टेट में जो कंपाउंड्स है, फॉर एग्जांपल क्रोमेट, डिक्रोमेट, क्रोमियम के ऑक्साइड्स हैं, वो एम्फोटेरिक नहीं होंगे. सिर्फ ये ऑक्सीडेशन स्टेट के कंपाउंड्स ही एम्फोटेरिक होंगे. इसको आप डायरेक्टली याद कर सकते हो. नेक्स्ट कुछ मेटल्स हैं जिनके सारे ऑक्साइड्स एम्फोटेरिक होते हैं हमेशा. फॉर एग्जांपल जिंक, Sn, बेरिलियम, राइट, एल्यूमिनियम, lead. So these are some metals that you can just directly recall: lead, gallium, cadmium, right. So इनके जो सारे ऑक्सीडेशन स्टेट्स हैं, all OS means all oxidation states are actually amphoteric, right. So this is something that you can remember and this is something that you can remember. And the amphoteric oxide से related बहुत questions आते हैं और जितने भी questions आएंगे, all questions you will be able to solve them, right. So sorry, so let's just move to the Next concept, acha, when we are talking about the neutral oxides, so in our syllabus we will able to remember three of them that are more than sufficient. CO is neutral, NO is neutral, and N2O is neutral. Always remember CO2 and NO2 are not neutral, they are somewhat acidic. Next is when we are talking about metals. Okay, so metals when they are in oxidation state of, so there are three oxidation state possible, maybe they are into +1, +2 and +3. so when these are the oxidation states, they mostly and 99% of the times they form basic oxides. When they are metals are into +4 oxidation state, they somewhat form amphoteric oxides. We are usually talking about the transition elements, for example ki MnO2. so MnO2 in manganese, the oxidation state is +4. so when transition elements or when transition metals are in oxidation state of +4, they'll form an amphoteric compound. Next is that acidic oxide, when the metals are into +5, +6 and +7, so they will form the what we say ki acidic oxide. so this is also something that you can remember, right? 5, 6, 7 and oxide of metal are acidic, +4 oxide of metal is amphoteric, and 1, +1, +2 and +3 oxides of compounds are metals, right? so that's it. Next is the example can be very simple. CrO3 is +6 and it's acidic. Next is acidic oxide. I think non-metallic oxides are acidic oxides, and some oxides of metalloid oxides are also acidic oxides. You can just remember some examples of metalloid के oxides which are actually acidic, right? You can just remember them directly if you want. अच्छा, हम लोगों ने उस एलिमेंट्स के ऑक्सीडेशन स्टेट लिखे हैं कि कहाँ कहाँ पे वो एम्फोटेरिक होते हैं, जैसे AS2O5 राइट इज एन कंपाउंड, और यहाँ पे जो ऑस्मियम है इसका जो ऑक्सीडेशन स्टेट है दैट इज़ +5. तो यहाँ पे जो AS2O5 है इट इज़ एसिडिक बिकॉज +3 पे क्या था, एम्फोटेरिक था. ये हम लोगों ने ऊपर सीरीज में देख लिया था. नेक्स्ट इज Sb2O3. Sb2O3 जो है दैट इज़ ऑल्सो बाई एसिडिक. Sb का जो कौन सा स्टेट होता है जो एम्फोटेरिक होता है वो हम लोगों ने देख लिया, दैट इज़ समथिंग दैट वी हैव कवर्ड. ACO2 इज़ ऑल्सो एसिडिक. GeO2 is acidic and TeO3 is also acidic. और इसके अलावा नॉन मेटल्स के जो ऑक्साइड्स होते हैं वो सारे एसिडिक होते हैं. फॉर एग्जांपल N2O5, CO2, NO2, B2O3 right. so that's it, that is about this video. Maybe I'll be able to clear all your exceptions. These are some by very generic questions that they ask directly. the electronegativity का जो ऑर्डर पता है उस पर डायरेक्ट क्वेश्चन आते हैं. इलेक्ट्रॉन एफिनिटी में एक्सेप्शंस बता दिए, उस पर भी क्वेश्चन आते हैं. और आयनेशन पोटेंशियल का हाफ फिल्ड फुल्ली फिल्ड से कर सकते हैं. जो एक्सेप्शंस बताए हैं मोस्टली जो PYQs हैं अभी तक जितने भी क्वेश्चन आए हैं वो आप सिर्फ इस सेशन से ही कवर कर सकते हैं. सो दैट्स इट, दैट्स ऑल फ्रॉम माई साइड. Maybe you have enjoyed this video. So that's it.